I work at NRG, working on thermohydraulic analysis and doing simulations of accidents, including design basis accidents and also severe accidents. The presentation I have is, I'll try to show you something of the design of the molten salt loop. Well, you've seen the presentation on that loop yesterday, but that one was shown a little bit from the outside, and I will be trying to show a little bit from the inside how it was how we were designing it. We want to place it next to the high flux reactor core. And we've been designing it for the past couple of years, and it's a complicated thing. We wanted to have a design that is feasible. We can prove that it will work, and furthermore, we can convince the Dutch authorities that it is safe. It's a combination of different expertise. So we had a team of different specialists. The main task is the engineers who were actually designing the whole thing. The neutronics team was calculating the power that's generated, that will be generated. We, the thermohydraulic guys, were taking the design and modeling it and trying to give them some feedback how it looks from our side. There's also a chemical team, and there's another safety team who was working on the postulated initiating events to have some first attempt to get the pi for this loop. We, the thermohydraulic guys, sometimes I asked, what are you guys doing? So I would say that we build a model of whatever it is, whether it's a power plant or it's a loop like this one. And we use tools that allows us to analyze transient behavior of such a facility. So basically we build a model, we have this power plant, and we make a hole here and there, see what happens. It's always a lot of fun. So in this case, we didn't get to the pi analysis, we just defined the pi, so we didn't get to the accident analysis. Our work was basically to do design support. So what happened was that the engineers were setting up the first design of the loop, and then we would model it in our tools, and then we would try to analyze what will happen. And then we would get back to them and say, okay guys, you need more heaters because you're never going to be able to heat it up to the desired temperature. So they say, well, we have difficulties to put more heaters because we don't have much room in there. So we actually put more of an insulation around it, and that should work as well. So they would give us a new design, and then we would analyze it again, and then we would say, okay, well, this thing can be heated, but it's going to take 125 years to do it. So you're going to have to put some more heaters anyway. So that's more or less how it looked like, and it's been really enjoyable and pleasure to work with good specialists to design the loop. Just to give you the impression, we first designed this loop in 2016, and we had a ready design, which you can see here. It was a 500 kilowatt thing. We could generate 500 kilowatt. We designed everything was fine. However, it turns out that it's not possible to do it. There are some other restrictions which are related to the reactor safety issues, and we had basically to reduce the size of it. They told us that you cannot do it like that, you just have to make it smaller. So in 2017, we made it smaller, and also we had to reduce the power. So we went from what we were aiming at was 500. We had to aim at 125, roughly speaking, 125 power kilowatts. Okay. So the way it looks like is you have the fissile region, which is here. And that's coming close to the HFR so that you can use the neutron flux from the reactor, because the salt will be subcritical. So the idea is we don't go critical, we have a subcritical system. We can keep it running using the neutron flux, so it's coming close to the HFR reactor. And then the neutron flux is starting the reaction, and if you want to shut it down, you just move it away. It's only a few centimeters, as actually you need to move it. It's very clear effect for reactivity. So we have basically, we have this place which is, the reaction is coming. We have the salt tank at the bottom where the primary pump is located. We have the heat exchanger, which is here. It's we call detachable heat exchanger. We can put it in, go it out, so we can detach it during the startup when you need to insert power to preheat the whole facility, and then it's coming in during the operation when you need to cool it down. So the flow is from the salt tank. The flow is here, going up through the heat exchanger, going back into the salt tank. What's not drawn here, that there is also a dump tank below. So there is a tank where you can dump the salt and put it down. It's also in case of accidents, that's one of the safety measures. Now this whole thing has to be sitting next to the HFR reactor. It's a high temperature salt, and it has to be placed in a big pool of cold water. So we have here three containment. We have this triple containment that's designed. The molten salt is circulating of the first containment, which is made of hastelloy. The second containment is made of steel, and with a low pressure argon in the space between the first and the second. And the third containment is made of aluminum, and pressurized helium is in the space between. So that you have to have different gases for leak detection. We need to have different gases in the different spaces. And aluminum is immersed in the HFR pool. A few words about the heat exchanger. As I said, we had to reduce the size. So we had to go from a typical classical shell with multi-tube heat exchanger to something that was never designed before. It's our own design, which is plate to plate, and those plates are movable. So we can move the plates, and that way we can control the power. We have the salt tank here, which is filled with salt, and during the startup, the whole inventory is more or less the whole of this tank is filled with salt, and then we start up the pump. Part of this salt is pumped through the loop, and the salt level will decrease here. The space above this salt is occupied by the neon gas. So what we are using, as I said, we're using the system codes. I don't know if you know anything about things like RELAP or MELCOR, which is the US NRC codes for safety analysis. That's what we use quite often. We use RELAP for HFR safety analysis and MELCOR for severe accident analysis. For this thing, we were using our own spectra code, which is similar in terms of the modeling. So it's a two-phase water, non-condensable, and also different liquids, they're different than steam and water. So we can analyze the molten salt liquid metal reactors, and also we have this fission product transport model in it. I was recently busy with validating the fission product transport using MSR data. That's quite interesting. It's difficult because there is so many things happening in these fission products. They migrating to graphite. They are moving, attached to the bubbles, and you have to, when you're modeling the whole thing, you have to tell the code more or less how this phenomena. So the code gives you some Sherwood number correlation. You have to fit in the coefficients, and that's why I was so excited hearing this presentation of Elisa this morning, that she's doing experiments that will allow me to understand more what's happening, how fast noble metals are migrating to the bubbles. Okay, but that's a bit of a side activity related to the modeling of for the future, to the modeling of fission products. Right now, we just set up this model, as I said, to do this design support analysis, and sort of like you have to take the geometry, you have to modelize it somehow, and this figure is showing you more or less how the model looks like. Then our neutronic colleagues were calculating the power generation. So you have to keep in mind that because it's next to the reactor, there is a lot of power being generated in the materials due to irradiation. So the one thing is that the fission power is generated in the salt, but the irradiation power is generated in all the materials, not only in the salt, but also in the containments, the first and second. Actually, the first containment gets most because it's closest to the reactor. So we calculate those power distribution due to nuclear and due to irradiation. And then we do the simulation. So we try to develop a feasible startup procedure first. So we precondition the thing using the heaters. I was saying we had to design the heaters that will allow us to heat it up in the reasonable time frame to the desired temperature, so that when we start pumping the salt, it's not going to freeze anywhere. So we have this first stage, we preheat it using the external heater. Then we fill up the salt, start up the normal situation. So we insert the plates from the heat exchanger. We have it running. And yeah, these are some results from the preconditioning. You see, we do have to. Yeah, we design it for 8 hours, but it's not. I mean, it's from thermohydraulic point of view. So this is just to looking at the balance of heat and heat losses. There might be other restrictions like the allowed from the material point of view, the temperature gradient that's allowed. So if you need to make it slower, it is. I mean, the fastest we can do it is in 8 hours. That's what we checked. And then it comes up with stationary situation and with some heat losses, which amount to about 5 kilowatts. So that's what the heaters have to compensate. The heaters have to have more than 5 kilowatts because you need to preheat it and you need to keep it running. These are some results from the filling up. So we assume that the power is linearly increasing in some time frame when we start the nuclear reaction. So we assume that we move it close to the HFR and it's coming to the desired power. And we calculate the temperature behavior and the whole behavior of the whole system. So, and I was saying irradiation power, it's about 40 kilowatt, and the total power that we were able to run, that's 145. We're aiming at 125. We checked that 145 was still feasible for this design, so that's good. but the design we aim is 125. But the thing is that you can see it's quite significant here's the irradiation power. So if you fill it up with salt, of course, then the heat losses are becoming larger. So in the 5 kilowatts during preconditioning, 11 kilowatt during the normal operation. And one thing that we observed is that, I'll show you a little bit here, what happens, you start up the pump, you have the salt here, and the salt is pumped here through the hot legs of the cord and this pipe, then it enters the heat exchanger, and then it has to like push this gas away, and then basically we want the gas to be pushed here, the neon gas, but it doesn't really want to flow that way because it's a sort of two-phase mixture and the bubbles are being trapped and it takes a long time. And also our code is not a detailed CFD code. If you know about system codes, it's basically 1D two-phase flow. We feel that it's not accurate enough for this kind of situation. So that's one open issue that we have, is to analyze this purging the gas from the heat exchanger with the CFD. That's one thing that we wanted to do, and we still want to do it in the future. We didn't have time to do that. So that was this part. Another part that we had trouble, we didn't manage to solve till the end, is that the heat up of the second containment. Now, as I mentioned, there are 3 containments. So here's the salt inside. You have the first containment, then you have the middle containment, and you have the gas, so argon and helium here. And then you have the aluminum third containment, which is in the pool. So the third containment is cooled by the cold water in the pool, so that's not a problem. The first containment, it's about the salt temperature, it's not a problem. The middle containment, it's getting a lot of irradiation, and then therefore it's heating up quite large, and we just could not get this temperature. I mean, we calculated the temperature behavior during normal steady state operation. It was too high. So this was a calculated temperature for the first and the second containment. So you can see that the second containment was clearly the temperature was higher than what we got from the engineering, that it's allowable for this kind of material. So we have to work on that, and obviously we need to do some forced cooling here. We didn't have time to finalize this, but apart from those 2 issues, we feel that this whole loop is pretty much designed. We need some small things to wrap up and to improve. Okay, we have a design that we feel is feasible with some improvements, and the design is intended to provide a test environment for material testing. We did some design support calculations, and we found out that we can have it up to 145 kilowatt, and we need to verify the pump filling procedure, because I mean, in the past we had here a simple solution to that. So we had a valve here that would allow us to get rid of the gas, but it's not possible, unfortunately, for some other reason. The simplest thing would be to let the gas out, and but no, there are some safety issues and also some size issues of how we wanted to make it, and that was much easier in the previous design concept, but with this latest design concept it was much more difficult to design. So this is still an open issue. It's something that we need to, basically we want the salt to push the gas into the pump, into the salt tank, and the gas has to be pushed downwards, and we don't know if that's going to work. We want to study this, and yeah, and leftover issue was that additional cooling. So I would say, yeah, that's what I was trying to show you, that we have already designed, and it was a pleasure to work on that for the past couple of years. And for the next design phase, well, that's the story that Lucas was mentioning already yesterday. We need to find some collaboration to continue this work. Okay, thanks for the attention.
Yeah, we have questions for Mark. Yeah.
Just a comment, your problem about getting the air out of the heat exchanger. I'm 100% sure you would be able to do that, but you can verify by building it out of with water and simple plastic tubes, and then you can verify that within 1 minute. I have a question about the insulation between your second barrier and the aluminum barrier, where you have the water. What insulation are you using there?
I don't remember that. I would have to check that. Because you know that there is one thing that there is, the insulation is not everywhere. I mean we cannot have an insulation in the hot leg where the core is located, because then it's very close to the reactor. It has to be very close to the reactor, because otherwise it doesn't have enough neutron. So the insulation is not everywhere, and it's only in some selected part. The heat exchanger, obviously, the heat exchanger, the pump tank is insulated. And no, at the moment I don't remember the material. That I can check it and get back to you.
You mentioned that the heat exchanger was a plate exchanger, but in the code it was modeled as a simple flat, or how did you model this in your code? Did you have any specific attention to that, or any difficulties?
For one thing, the drawing here, it's sort of like, you know, it's an arbitrary drawing. We draw it like that because that's what we think is the best illustration of what it does. So basically, the way it works, it's a plate, okay, but you have two plates next to each other. But if you look from the side, and if you cut it, you'll see that the plate is separated by some nearly horizontal baffles, or whatever, some horizontal, nearly horizontal plate. So they would direct the flow to go a little bit left and right. So that's how it, and it happens like that inside and on the outside. So if you look next to it, there is a cooling water plate, and then the water is doing the same from the other side. So that's more or less why it's drawing like that, and we try to model it. And the thing is that you have also a bit of difficulty in modeling it, because in the transient you take the water cooled plate out, and what's left is the salt plate. So in the same, you have salt plate radiating to the next salt plate, and that's basically give you no heat transfer at all. And then you insert the water-cooled plate in the middle during the transient, and then you start exchanging heat. So it's also a bit challenging for our codes, because the codes are not really meant to analyze a situation where the geometry is changing during the transient. But that was the design, that was the only feasible design for this kind of, with the restrictions we can have. So it's a little bit of funny, an unorthodox design of the heat exchanger, and but that was keeping us out of problems because of the size and the amount of power that we needed.
I understood that there will be constant measuring of several aspects while the loop is running. Can you tell a bit about which parameters will be measured while the loop is operating?
Well, the loop is designed for material testing. So obviously there is an instrumentation which is in the loop, in the part which is next to the reactor, and I cannot tell you any details because that's not my piece of field. I only remember from the discussion that we needed to design this part with certain geometry to allow for instrumentation. So that I know that this part, which is next to the HFR, so basically this hot leg, which is next to the core, if you look here, if you look inside, it's like you have those three containments, and then inside, okay, there's a better place here. Yeah, here it is. You have the triple containment, and you have this space where you have the salt. But this is not empty as it seems here. There is a thing made of, actually I don't remember the details. I remember that there is this whole thing which is made for material testing, sort of a holder where you can put materials, and that's also some instrumentation in it. But there is, I'm sorry, I cannot give you a really good answer to that, because then you have to ask our colleagues who are more, I'm just, taking the design and see how it runs, and I don't care what's inside.
For the material testing, what is very important is to understand if you do the experiment in situ or outside when you have finished the treatment with the molten salt contact. So what is your vision of the material testing? In situ measurement or ex situ?
I think that the best answer is here. We need to think, if we have some, I think the design is flexible enough that we can do both eventually, with some small adjustment here and there. But at the moment we wanted to have a feasible design and something that we can present to the authorities, and then at least be able to discuss the safety issue, because that's also a major issue for us. Anything we put next to the reactor is very difficult to get a license. So in order to put such thing next to the reactor, we see that it's gonna be some trouble. So we put a lot of effort into this safety analysis. But the design is, we wanted to have a rough design that we know it can work, and then we can tailor it to specific needs in the future in collaboration with someone. So if you have any suggestions, I think that, we are very interested in discussing this.
So you are using a plate heat exchanger, and imagine that the distance between the plates is rather small. What precautions are you taking to prevent plugging of that heat exchanger?
You mean plugging by solidified?
Plugging by means of contaminants. In sodium they did more or less the same, but they got the problem of sodium oxide precipitation and actually plugging the small distance between the plates, reducing the thermohydraulic efficiency of that thing.
Okay, and is that some published material? Is that available material? That's what you're talking about?
No.
Okay, well, we will have to check that. I mean, that's might be a problem, and indeed the distance is not very large. I don't remember at the moment how much is the distance. I think, no, I cannot say. It's order of millimeters, that's for sure. Yeah, and then it's going out, coming back in. So yeah, if there is any information like that that would allow us to do some estimation on this problem, then I'll be much obliged if you could share that with us.
Let's thank the speaker again.